Hey guys, so today we're going to be deriving the transfer function for a second order active filter. And we're going to begin by simplifying the circuit diagram, because it's a bit confusing when you look at it initially. So the most obvious thing we can cull is this V out up the top here. It's not connected to anything else, there's no closed loop, therefore the potential at this second point has to be the same as the other one, and we can just get rid of the lamp wire. It's just hanging about in the way. So next is we're going to treat these op amps like they're ideal, and we're going to assume no current flows in them. So we can pretty much axe those inputs into the op amps. And so what we'll do is we'll erase them, and I suppose we'll just maybe use connected dots or something to show that they're physically there, but we can pretty much ignore them. So we know that the V out up this top point has to be propagated through because the op amps will hold the potential the same at both sides. So these are all V out, and we'll label this one VB and this one VA. And now we'll start identifying some currents through it. So we're going to have a current into V in. There'll be a current down through C1 if we say I1 goes there. So the next easiest are these ones down the middle. Because we assume that no current goes in the op amps, we can say that those two are equal. And it'll just go whichever way we choose. And here, once we identify R4, since there's only one sort of input into here and it goes down to ground, I4 has to equal I5 and I6. So that's probably the easiest part to start at. And so that's what we'll do. So we'll say I4 equals I5 plus I6. And now we can start identifying some of those terms. So I4 is going to be the voltage across it, which is VB minus V out, over R4. And that's just the same as Ohm's law. Like normal Ohm's law, I equals V on R. So I5 is much easier. That's just going to be V out minus 0 if you want to go nuts, over R5. And I6 is going to be just the normal current through a capacitor, which will be C5, and then the change of voltage over the capacitor with time, which we're going to call d C5 dt. So now we can substitute some of these in. So we'll do our VB minus V out on R4. So this is the part where I kind of tediously just dump these in, and that just disappeared because I saved having you guys watch me erase all that rubbish. So now we're just going to kind of rearrange it a bit so we can group some of the like terms, and that'll just make it easier to deal with later on. So you can see here these two V outs, their denominators we'll be able to group together, and the rest is as it is. And the R4 and R5, you'll just cross multiply in order to get the denominator the same here, which is what we're about to do. So you'll end up with your R5 plus R4 over R4, R5. Pretty standard stuff in that regard. Cool, so now we need to find VB, because it's something we really don't know here. And so the only other option we've got, because we don't know the current that's coming out of the op amp, is to look at I3, which is going to be that center voltage minus VB over R3. And because that's going down that line and we're assuming they're ideal and there's no current going into either op amp, we can say that I3 is going to be equal to I2. And that's using Kirchhoff's current law. So we're saying that the sum of the currents into this node has to equal 0, so they've got to be equivalent. We're going to simplify this and just move the R3 to the other side. And rearrange this so we've got it in terms of VB, so we can substitute it back in. And I3 isn't going to be terribly useful to us, so let's replace it with I2, which we still have more terms so we can figure that sucker out. And so now, bing, we've changed screens. So the top one is the equation we just worked out, and the one below it is the equation we'd worked out previously. So now we can solve everything here except we need to figure out I2, and it's worthwhile doing that before we substitute. So I2, we can say here, is going to be equal to VA minus V out over R2, which is standard. It's exactly the same thing we did for I3. But that's left us with another thing we need to figure out now, which is VA. And VA is the one that kind of, I know when some of my friends were doing it, and myself, we all got confused on this part here. So the trick, if you'd call it that, is to just recognize that VA is equal to V out minus the drop across C1. So we can say that that drop, or the potential across it, is going to be V out minus VA, which is exactly what we've been doing for all these other resistors, and then just rearrange that to get VA. And this is neat because we know all these things at this point. So while we don't have a value for VC1, we'll be able to work that out pretty quickly. So we're just substituting in this value for VA into I2, so the two V outs will cancel. You can see V out minus V out, which is going to give us our minus VC1 over R2. So this is cool. We can substitute this in to the top equation, and we pretty much know everything there. VC1 is pretty straightforward to figure out, and now we have everything in terms of voltages, which is what we wanted. So I probably should have said that earlier. What we've been trying to do is get these equations in terms of voltages that we can figure out or know. And I've just magically, bing, tidied everything up. So this is what we'll use pretty much for one equation, and it's second order, so we'll need a second equation, and we're going to use the input for that, because we're deriving a transfer function. Somewhere in there we're going to need V in. So let's look at I1, which is V in minus V out over R1, and instead of using our minus VC1 on R2 value, let's use the actual current through a capacitor formula, and equate it like that. So now we'll just tidy these up a bit and rearrange. And now we're going to start by substituting in our value for VB into the top equation. So we only have two equations we need to deal with. I'm leaving off the R4 here because we'll just multiply that on the other side, which is nice because, as you can see here, it's going to cancel the bottom of here, and we'll just place it up there. Great. So now we have one equation, and now we're just going to rearrange that, again grouping like terms together. The reason we've been after VC1 and VC5 is when you've got active components like these, apparently they're called state variables, and it gives you an idea of pretty much how many equations you're going to need to solve this sucker. And if you can get it in terms of them, it's pretty easy to do a Laplace transform, which we're about to do, and pop out the equations. I'm going to try and do this without matrices. So because we're doing a transfer function, all the initial conditions are going to be 0. And so for the derivative terms, the Laplace will just be s times whatever it is to the s, and for the normals, it'll just go to the s. Makes it pretty easy to do. You can use matrices to solve these things, and I like doing it that way, but we'll save that for another video. So we'll start off this equation, nice general one for the initial Laplace. So it just goes to v in of s minus v out of s. I thought about doing a Laplace explanation, but I mean places like Khan Academy already do that better, and they can do it better than I ever could. So you can see what's happened here. The derivative would normally have a like a minus v at 0 term, but transfer function, so we don't need it. Cool, so this one here has given us a value for VC1 of s, and we know VC5 of s is just v out. So we can use that VC1 of s as kind of the common link between the two equations. So now we'll rewrite it out in terms of that. So we've got a term to substitute into this second equation. Well, I have no idea why this is sitting here for so long. Cool. So now we can simplify this further. Keeping it as 1, we'll just replace it with R5 on R5. And once we do that, you'll be able to see that the two R5s on the top will just cancel out. Cool, so now we've got this VC1 here, and we've already solved for a VC1 up the top. Oh no, apparently we're taking the Laplace transform. Same step we did earlier. We'll just rearrange this sucker a bit. So we'll put the R4, R5, or C5, R4, C5 back in. And the derivative just turns to S, V C5 of S. And VC5 of S is V out of S. If you look at that node where I4 meets I6 and I5, there's no one else it could be. Which is cool because it's going to allow us to group some more of these terms. Great, so now what we need to do is put in VC1 into the equation and then rearrange for our transfer function. Cool, and we're done. So we're going to rearrange this further just because some of the textbooks you might use at uni will have standard forms for like second order, high and low pass, band pass, and all that sort of thing. So we're just going to get the formula to look like one of those, and that'll allow you to do some more stuff with it for your course, maybe if you've got a lab report or whatever that wants them in that form. And it's pretty straightforward. we've got to get s squared on its own, so we're just going to divide by everything in front of s squared on the top and the bottom. So what we're going to do now is just, if we erase the s's and we replace them with j omegas, we'll just think about what this thing's going to do in terms of frequency, which is the omega, and work out what kind of filter it is. So that whole thing was squared there with the j. And so j squared is your negative 1 square root squared, which is just minus 1. And now if we think about it, at low frequencies, those things are going to go to 0, the omega terms, and you're just going to get a constant on a constant. But as omega goes to infinity, which is we're looking now, the denominator is going to get really large, which means this thing will get really small. So it's a low-pass filter. Yeah. And that's that. Thanks for watching.